All right, so here we are, the last section of chapter 10, section 10.6. This is bond enthalpy. And so bond enthalpy is a measure of the strength of bonds, the strength of bonds within a molecule, which ultimately determines the stability of that molecule. Bond strength is measured as bond enthalpy, the enthalpy associated with breaking a specific bond in 1 mole of a gaseous molecule. So the exact bond enthalpies can be measured for diatomic elements. Most bond enthalpy values, however, this is in contrast to that previous statement about diatomic elements can be measured exactly. Most of these are just averages. So as you see here, we've got a wide range of bond enthalpies. Those associated with hydrogen-containing bonds, carbon, nitrogen, and oxygen-containing bonds. And they range from the H2 bond, which is 436, all the way to HS, which is 340. And then sulfur-containing compounds or sulfur-containing bonds, 340 all the way down to 225, and then halogens and multiple bonds. Okay, so one thing that we'll get into is multiple bonds. So carbon-carbon bond or carbon-carbon double bond, we can compare that with a carbon-carbon triple bond. The double bond has a bond enthalpy of 611, the triple bond is 835. Okay, so the single carbon-carbon bond is something like 349. I can't remember exactly what it is, but it's considerably lower than that. So essentially what that tells you is the more bonds that there are, well, the higher that bond enthalpy is going to be. So effectively, the stronger that is going to be. Now, you can see that same trend with N2, or a double bond between 2 nitrogens and triple bond between 2 nitrogens, 418 to 941. Now, bond enthalpy is also correlated with and can be related to bond length. So covalent bond length is the distance between 2 nuclei of 2 atoms that share electrons in a covalent bond. Our published bond lengths are average values obtained from the measurements of many different molecules that contain bonds between the same pairs of atoms. Now you can compare bond lengths and bond enthalpies between the same 2 elements to determine the relationship between bond length and bond strength. In general, here's arguably the most important part of this slide. As bond length increases, bond enthalpy decreases. Okay, so longer bonds are weaker bonds. So the way I always kind of think about it is, and not that this is an example that really I can relate to necessarily, but I think about like a canoe. If you have a canoe and you use a single rope to attach it to the pier, well, it's going to be, let's say it's 10 feet. You have a 10-foot length of rope that connects that boat. Okay, so that boat is going to kind of drift all around, but it's going to stay no more than 10 feet, it's going to drift no more than 10 feet from that pier. Okay, now with that same length of rope, if you double it over, so what that means is you take the side that's hooked to the boat, you throw part of it to the pier, and then you have it thrown back to you. What's that going to do? That's going to pull you on the boat closer to the pier. And so that's going to be 2. Well, that 10-foot length of rope is going to be cut in 2. And so the strength with which that boat is held to that pier has gone up. The length of that bond, or that length of that, or the distance that boat is going to be from the pier, has been cut in half. And so now if you were to do it one more time, now you've got like 3 lengths of rope effectively. So you've got 3 connections between the boat and the pier, but they're shorter. So it's ultimately a stronger bond between the boat and that pier. So here we see that trend, bond lengths. Well, we've got all these single bonds between hydrogen and other elements. Then we see multiple bonds. Okay, I'll circle this one and, oh, actually, no, I'll circle, yeah, this one and this one. A double bond, is 133 picometers, a triple bond is 120 picometers, so they got shorter as they move closer together. All right, now this is going back a moment, but based on bond enthalpies, which is going to be more reactive? Hydrogen chloride, HCl, or HBr? Now this is a question of bond enthalpies, and basically, well, which one of them is going to be more reactive? And the answer is HBr, because this is going to have a lower, I'm just going to shorthand that as BE, bond enthalpy. So the lower the bond enthalpy, the more reactive that substance is. So that's, yeah. So that's kind of the trend that you want to follow. Now, bond enthalpies we can relate to reaction enthalpy. So bond enthalpy values can be used to estimate enthalpies for reactions involving molecular compounds in an application of Hess's law. It's useful to answer certain questions before carrying out a reaction, such as, will a proposed reaction be exothermic or endothermic? And how large will the energy change be? Okay, so our steps that we use to estimate reaction enthalpy from bond enthalpies. We want to calculate the total energy that would be added to turn the reactant molecules into individual atoms. So bond breaking is going to be an endothermic process. Now we calculate the total energy that would be released with these atoms combine to form product molecules. Bond making is an exothermic process. So these two keys, bond breaking is endothermic, bond making is exothermic. So effectively what we get is this equation right here. Delta H sub Rxn. So the enthalpy of our reaction is equal to the sum of the change in enthalpies of our bonds broken minus the sum of our enthalpy changes of our bonds formed. So a sample calculation for this would be looking at this reaction right here. H2 plus O2 yields 2H2O. Okay, now this is a balanced chemical reaction, but what we want to do is we want to think about which bonds are being broken and which bonds are being formed. Okay, what we've got is we've got 2 HH, so effectively HH plus HH plus O, that's a double bond there, and we're going to form OH, OH, OH. So that's what we're doing. We're breaking 2 hydrogen bonds, which is signified right here, and we're breaking 1 oxygen double bond. And so we get the sum of the bond enthalpies of HH, 2 of them, plus the enthalpy change of an oxygen-oxygen double bond, and we subtract from that 4 times the change, or the enthalpy change of OH. So to plug those numbers in, we get 2 times 436 plus 498. So we added those numbers together, and we subtract from that 4 times 460. So our change in enthalpy of the reaction is 1370 minus 1840. And that gives us a delta H Rxn of negative 470. So if you remember this right here, and then you think about the reaction that's at hand, so what are the bonds that are present in that molecule? What are the bonds that are broken? And then subsequently, what are the products that are formed? What are all of the bonds involved in that? You're going to be in great shape for this sort of thing. Now the key, so that's an important takeaway of this. I would argue that this takes us back to one of the important skills that we've already been exposed to, and that was that takes us back to one of our skills of drawing a Lewis structure. Because if you can draw a Lewis structure of a molecule, then you can identify which bonds are present. And therefore you can say, okay, well, if I look at H2 and O2, I only had hydrogen-hydrogen and oxygen-oxygen bonds. My product has H2O. Therefore, I've got 2 OH bonds that I need to form. So it helps you kind of visualize that. All right, well, that's all chapter 10. I hope this is good. You got this. You're going to do great. And I will see you in chapter 11. Isn't that a bankruptcy thing? So let's rephrase that. I'll see you in the next video when we begin talking about our material for chapter 11 of General Chemistry 1. All right, have a good one, y'all.